speaker, which is Maarten van der Zee, a senior scientist on bio-based products at Wageningen Food and Bio-based Research. He's also been working for more than 30 years in this field. And he did a PhD on structural biodegradability relationships of polymeric materials, and now primarily executes and manages research projects in the field of biodegradable and or bio-based products at Wageningen Food and Bio-based Research.
Okay, thank you. So indeed, I'll kick off this this webinar with some we're talking about biodegradability and the state of play. Before I do that, just a few words about the organization I work for. Wageningen University and Research comprises the Wageningen University and 8 contract research institutes. So I'm working for Wageningen Food and Bio-based Research that is working on the topics that you see listed here, including renewable materials and bio-based chemicals. We work on projects in the whole chain of these products, starting from the feedstock, processing technologies, and also towards its application. Zooming in the group of sustainable plastics technology, we have a over 30-year track record of working with bio-based materials, 10 years of expertise in recycling technologies, and always working with various processing expertise in various processing technologies and material analysis, including biodegradation, which is the topic of today. So in this, about 20 minutes, I'll talk to you about what is biodegradable, what does it mean, how is it measured, and some key aspects in common misconceptions. And then Astrid will continue with more examples from practice and things like that. So to begin with, defining biodegradability. What does biodegradable mean? Well, strictly speaking, it is the ability to biodegrade. But at this point, it's good to realize that the biodegradation process is comprises of very many steps. And you have steps from polymers going to smaller oligomers to monomers to biochemicals that can be taken up again into all kinds of biological processes, and ultimately to the minerals, mineral components of the materials that it is comprised of. So carbon dioxide, water, methane, things like that. So the terms used for different steps actually. Also good to realize that these different steps, enzymes or microorganisms can play an important role in these steps in biodegradation, but also physical processes, UV light, temperature, shear. In some of these steps also interact and play a role, and they cannot be separated clearly. But when you talk about the whole ultimate complete biodegradation to its minerals, that's in biology, that's also referred to as mineralization. So the term you see here, when you have materials that physically fall apart, that is referred to as disintegration, which can be triggered by biodegradation, but is more usually the first step of biodegradation. And biodegradation is the term used actually when we're looking at degradation on a chemical level. And you also sometimes refer to it as this process can be put into a formula, and we'll come back to this where material is transferred to as a reaction transferred to its intermediate reaction products and its ultimate degradation products. Second important point to realize when you're talking about biodegradability is that it's typically a system property. And what do we mean by that? Well, it's quite obvious that the the chemistry of a material, of a product, the type of chemical bonds from which it is comprised really determines whether something is biodegradable or not, whether it's susceptible to microbial attack or to enzymes, whether it can be hydrolyzed or things like that. It also determines more morphology also, so these chemical bonds, how they in the material they can form through hydrogen bonding, or they can form crystallites and hard and soft domains, amorphous domains. That all relates to the properties of a plastic or of a material. But obviously that also can have impact on how susceptible it is to biodegradation. But besides being a polymer property or a material property, it is also much depending on the environment in which this occurs. So mainly related to the activity of biological systems. So the presence of organisms, the availability of oxygen, all determines whether this happens, yes or no. And it's not difficult to imagine that you see here two pictures, that the same material will biodegrade very differently in a very dry desert, or in a warm, wet, lively rainforest. And that also has consequences in how we look at biodegradability. Because these are extremes, of course, but also in realistic environments where materials end up, where biodegradation can take place, we have differences in the environments, and they can be either be controlled environments, which we have designed for wastewater treatment, for example, solid waste, municipal solid waste conversion, composting, but also more uncontrolled open environments, either through litter, which really is uncontrolled, you don't know where and when it ends up, but also in more controlled ways, like fertilizer coatings used in agriculture, or mulching films and things like that, where it is in a controlled way, enters in a more uncontrolled environment where there is weather and rain and sun and things like that. And also in controlled environments, and in all these environments, you see there can be significant difference for the biology, whether there is water present, yes or no, or oxygen present, yes or no. Biodegradation will happen differently. And looking in, when you're looking at these different environments, and generally you can say compost is the most aggressive environment, and marine water is on the other side of the spectrum. So biodegradation rates will differ greatly within these environments, related to the type of micro and the activity of the biology. So obviously that also needs to be taken into account when measuring biodegradation. But first, how can you measure biodegradation? Well, I like to refer like biodegradation process, like any process, you can follow the equation, what happens. So common approaches to follow that is either you follow what happens on the left side of the equation, the depletion of substrate or the changes in properties there. On the other hand, you can also look at what is happening on the right-hand side of the equation. So monitor the formation of reaction products or intermediate reaction products, or the accumulation of things, or the ultimate degradation products, carbon dioxide, or in case of anaerobic processes, you can also have methane as a product. And obviously, it depends on what you're interested in, where you look at. Are you looking at this because biodegradation is a process comprising many different steps? Are you interested in this first step, or are you interested in the whole process? Do you want to know whether it ultimately goes to? So there's many different methods, and you'll see that in scientific literature and publications and all kinds of papers, many different ways, people using very specific enzyme assays to look at effects of various enzymes, or microbiological techniques isolating microorganisms that can can degrade a particular polymer. The respiration tests are well known in this field because they gave the possibility to actually measure the final end product, so the complete conversion to carbon dioxide, so the completeness of the biodegradation. But there's also field experiments needed. So also related to the fact that these tests, the gas evolution tests, to measure this is usually measured on powders to actually follow the complete conversion. But with that test, you can't really see in what time frame does a product actually fall apart and loses its physical integrity, which you can do in the natural environment and field test or laboratory simulated tests. But on the other hand, you can also see that in this type of test, it will never be possible to see when things fall apart and you can't see them anymore. How can you demonstrate that it actually goes completely to CO2? So usually a combination of tests is necessary to get the complete picture. And this is also reflected in the number of methods that are actually standardized, standard testing methods by standardization bodies. And so that also reflects in the number of standards that are available for measuring biodegradation. You see it, I have a list, listed some of them, and you can see here it's divided over the various environments. So composting or marine environment at the other hand, or anaerobic digestion. But within an environment, you also have various tests, either looking at the disintegration or test methods looking at the biodegradation. And then you even see within one column, you see different standards which are related then either to its origin, which standardization body developed the work, the scope of the whether it's for packaging or organic compounds, plastics or lubricants, which can deviate not so much in principle, but in the specifics of the environment and the test you're looking at. Besides standard measuring methods, evaluating the biodegradation, specifying how you should measure, there's also standards related to, which are different standards, so-called product standards, which actually specify that if you measure, it should reach this requirement or that level or things like that. And those product standards are then so-called products that are on a product level, for example, compostable packaging, biodegradable mulch film. And they not only specify how you measure, but also what levels should be obtained. And most of these look at the threefold requirements. On the one hand, you have whether there's sufficient biodegradation on a chemical level, the completeness, how much is actually converted into carbon dioxide, and there's set limits for that. And the 90% limit is set to guarantee that it is completely everything is completely biodegraded, taking into account that some of the carbon will also be transformed into to biomass and other components that are already taken up in the cycle, in the biological cycles. A second requirement is whether the disintegration is sufficient, and that clearly depends on the type of product where you want the function of the product, which obviously is for a packaging you want to discard as compostable, or a compostable product needs to disintegrate in another environment and another rate than a biodegradable mulch film in soil. So there's specific requirements there. And a third one, which is also very important, is how environmentally safe, set specifications for the environmental safety. And that's also done in two ways. On the one hand, upfront, that it specifies that you're not allowed to use specific toxic components in the formulation of your product. There's limits to the use of particular heavy metals and things like that. And on the other hand, there is also a check built in that during a degradation, no toxic compounds are formed. As intermediate degradation products, if they are becoming toxic, that is checked afterwards, after and during exposure. So this is how these product standards are built up. I have some examples here for compostable packaging, for biodegradable mulch film. And well, you can look up these numbers. But it's also clear that different product types, environments require different specifications for things. Another aspect of this from the market, there's obviously a clear desire to demonstrate or be able to show, communicate that you comply with these standards, and that's why certification programs and labeling has been set up. But again, in the general and discussions in the public, you often see also confusion there. So what do these mean? What do the labels mean? What are the differences? What is the acceptance in the market? Obviously related to the fact that there are different types of products for which you need different types of certification, different standards. But this is also encouraged, this confusion, by companies or NGOs designing their own specifications and labels, and so the consumer can be really confused by the different amounts of labels that say something about degradability. But in this context, it's good to know that for biodegradability, in particular, the certification programs of TÜV Austria and DINSETCO and the US Composting Council are well established and recognized in the market, and also function well in business-to-business communication. Whether these labels are clear to the public, well, that's still doubtable. But the question is whether it needs to be there. At least it's good to know there are also other labels on the market, but it's always good to check whether these are actually based on recognized standards. Keep that in mind. Just an example of these certifications. So these are two different certification programs where you see the criteria for biodegradation, disintegration, and these can vary. For example, for a soil degradable product or for a home compostable product, there can be differences in specifications with regarding the maximum test duration. The required level of biodegradation is always the same, 90% as mentioned earlier, but the methods with which you can use to demonstrate this are specified, can be different, also testing temperature, things like that, just to give an example. And the reason for it, because they're different products, they need to have different use requirements as well. The standards you see in the public discussions, sometimes some criticism on that these standards are not always representative for what happens in real life, and that is true in one point, but on the other hand, it's also inevitable. I'd like to explain that with an example. For example, food, vegetables, meat, food products when you leave them on the kitchen table, or they will decay, degrade, rot quite rapidly, as you expect. But to slow down this process, or maybe even prevent this process, we can put it in the freezer. So the biodegradation process slows down a lot. But by doing so, does that change the classification if something is biodegradable? No, not really. And this principle you have to keep in mind when you're talking about biodegradable plastics. Biodegradation testing is really necessary at the laboratory scale to verify the biodegradability, the intrinsic biodegradability. But whether a biodegradable product will actually undergo the biodegradation in a real environment will greatly depend on the local conditions, like the example in the beginning, the dry desert, the Arctic, the glacier. We can still find wooden boats that have been lying on the bottom of the ocean for more than 300 years, still intact. Does that mean that wood is not biodegradable? No, it is biodegradable, but there are conditions where biodegradation does not take place, and that is for not only for the biodegradable plastic the case, but also for all natural materials. In fact, that oil has been that we can dig for oil is also all because of that. Not all organic matter has degraded in over those years, but some of it has been fossilized, not biodegraded due to the conditions. And that is why it's also important to recognize that using the term biodegradable has no meaning unless it is defined. It defines the degradation environment, the time and the rate of degradation, and the extent of degradation. And the unqualified use of the term biodegradable is wrong and should be avoided. And actually, this is also taken up in some legislation in more and more countries. So that. Another example, another aspect I'd like to address is the environmental impact of biodegradable products, because sometimes biodegradable products are advertised as the solution to all littering, but I'd like to illustrate that with an well, not so nice example. You see here in the picture, dog shit is really readily biodegradable, but as you know, it doesn't disappear instantaneously, and while it's there, it can still be a considerable nuisance. And that is also the case for plastic products. Biodegradable plastic products, even if it's been demonstrated that they're readily biodegradable, depending on where they end up, they will disappear more or less slow, but never instantaneously. And while it is out there, it can still be a considerable nuisance. You can see it, but we should also realize that these biodegradables, when they do biodegrade and they ultimately disappear, it's always better than and less environmental impact than when it is compared to the alternatives that do not biodegrade at all and stay there forever. Before I conclude, just a few words on some policy developments in this area. Well, the European Plastic Strategy, is driving towards innovation investments, towards circular solutions. You've probably all seen this picture before of the Ellen MacArthur Foundation about the new plastics economy, where the aim is to close the use cycle, also recognizing that there will always be some leakage out of this cycle, and some new virgin feedstock will be necessary. And well, they aim to decouple that from fossil feedstock. In that framework, so there's quite some efforts in improving and policy development towards improving the economics and the quality of plastics recycling. And there's also quite some work done on preventing plastic in our environment. So probably know about the initiative on the single-use plastics and the restriction on the use of oxo-degradable plastics, restriction of the use of intentionally added microplastics, which will actually will also continue, will be elaborated also on intentionally of plastics intentionally introduced into an environment, like mulching film, fertilizer coating, seed coatings. There's also good to realize that biodegradables can possibly play a role there as well. And this the scientific advice mechanism has generated a big report identifying several challenges and recognizing that biodegradables will never be a solution to littering, but it also acknowledges benefits to targeted biodegradable plastic applications. And well, that is good to realize. So in conclusion, I hope to have shown you that when you're looking to the application of biodegradable products, there are several factors you need to consider. For plastic applications, you always have the fact that the product, you want to have its functionality maintained when in use. But as soon as you don't need that functionality anymore and the product is not used, you want it to disintegrate instantly and biodegrade it complete ultimately in the real environment. And from as a material scientist, material scientists will recognize this is these are potential, these different requirements are a potential conflict, and it's always a delicate balance in trying to balance these things, but not impossible. Secondly, the key message is that communication with regard to biodegradation is key. It's good to realize that compostable is not the same as biodegradable in soil or in the oceans. That biodegradation in real life situations can be different from what is demonstrated in laboratory, but laboratory assessments are needed to demonstrate the intrinsic biodegradability, and communicating about that is key. And finally, by using biodegradable products, the impact on the environment cannot be prevented completely, but in specific applications, it will certainly lower the risk and the impacts significantly. Yeah, mainly because the shorter time of exposure that you get. And with that, I'd like to conclude this part of the presentation, and I'm open for questions.
Yes.